Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry lectures and solutions to homework problems. In this lecture, we are going to begin looking at the competitor to the substitution reaction. We're going to be looking at one of the reaction mechanisms of elimination. That is Elimination Unimolecular, or the E1 reaction mechanism. Now, I strongly urge you to, before you watch this Scribblecast, you actually look at the Scribblecast previously made concerning substitution nucleophilic unimolecular, or the SN1 reaction mechanism, because these two mechanisms are closely related. We're going to begin first by taking a close look at the steps of the reaction mechanism. Step 1 is referred to as ionization. It's sometimes called carbocation formation. Either way, it involves the formation of carbocations. So it's also called carbocation formation. Now I'm going to use essentially the same molecule I used for the substitution reaction mechanisms. I'm going to draw it a little differently for convenience, but I'm going to continue to use a chiral version of sec-butyl bromide, or 2-bromobutane. So here is my H. I'm going to have a CH2. CH2, CH3 here, and then here my methyl. Now in step 1, we have ionization where the carbon-bromine bond breaks. So I can draw a transition state. I'll do that. Where the carbon-bromine bond is being broken. Now I think I'll indicate that in red, if you like. Actually, no, I think I'm going to leave it as blue. So let's put some dots. These dots mean the bond is extending. It's beginning to break. Now the breakage is heterolytic. That is, both electrons go with the bromine. So carbon is becoming positively charged. At this point, it only has a partial positive, and the bromine is delta minus. The double dagger outside the square brackets that I draw, this double dagger, simply means transition state. And I'm going to call this transition state number 1. Because we have a multi-step process, we're going to have several transition states along the way. And I also indicate which bond is breaking. So I write here bond breaking. And identify in my transition state where the bond is actually being broken. So I show that. And when we are done, we end up with an intermediate species formed. I have to move this carbon over. That intermediate species you have an H here. That intermediate species is called a carbocation. It's sp2 hybridized and trigonal planar in shape. It is the exact same structure we drew in the SN1 reaction mechanism. And of course we have the free bromide anion. This step 1, if you compare it to the SN1 reaction mechanism, is identical. There is absolutely no difference between E1 and SN1 in the first step. Whenever you have a carbocation, you have to be concerned with the possibility of rearrangements. So step 2 is always rearrangement if possible. Now, if you remember the 1-2 shift discussion during the SN1 Scribblecast, you only do the rearrangement if you get a more stable carbocation. Rearrangements occur because they lower the energy, the overall energy of the intermediate. Now, the E1 mechanism differs from the SN1 mechanism in step 3. Step 3, our attacking group acts as a base instead of a nucleophile. And so in step 3, we call it base attack. Now, do you remember what is the difference between a base and a nucleophile? A nucleophile attacks positively charged carbon. A base attacks positively charged hydrogen. So the same attacking group can be both a base and a nucleophile, but in the E1 mechanism, it is acting like a base. So if I redraw my carbocation now, and I'm going to draw it at a slightly different angle. It's still trigonal planar. I'm going to just look at it from a slightly different perspective. It's the same carbocation, just looking at it from a different angle. And I'm going to focus on one specific proton, this one. And I'm going to have water as my base. It has lone pairs. Water can act as my base. I'm going to have my water go and attack the hydrogen. So it's behaving like a base. And remember, this is a carbocation, so there's a positive charge here. Now I can draw a transition state for this attack. Now I'm going to not draw it in this 3D shape. I'm going to draw it thusly. So this carbon is the carbon that originally has the positive charge. This was my carbocation. And here's the ethyl group. I'm going to give it an H. And this bond is breaking. And then we have the water. Funny, I'm going to run out of room, but that's okay. We'll make do. Okay, I'm going to use red to indicate bonds that are forming. So these bonds are forming. So I indicate bond forming. That's that guy. And that guy. And I also indicate bond breaking. That's that guy. Now this carbon right here was originally positive charge, but as the bond is forming, it's losing its positive. So it's just delta plus. As the bond forms to the hydrogen, we start forming, H2O starts converting to H3O plus, and so we end up with a delta plus here. So we have a delta plus and a delta plus. Now, running out of room, so I'm going to draw the product down here. Once we're done, oops, I forgot my methyl here. There we go. That methyl is this methyl here. Once we're done, we have produced this product. Okay. Okay. And of course, we also have the H3O plus that we've produced. And floating in solution is also the Br minus that formed when we formed the carbocation. Now what's interesting to note is in order to build this double bond, we had to pull an H off from a carbon next door to where the positive charge is. This type of carbon is referred to as a beta carbon. It's referred to as a beta carbon. Now beta carbons are carbons next door to the carbon bearing the functional group. In the carbon that originally bore the bromine, in this case the carbon bearing the positive charge is called the alpha carbon. And so you'll notice carbons attached to the carbon, the alpha carbon, there's more than one. The methyl is also a beta carbon. Now, in order to make a double bond, we had to pull a group off the alpha carbon. That was our bromine. We did that in step 1. And we have to pull a group off the beta carbon, which is our H. And that allows us to make this double bond. But one could ask the question, why did you pull the H off the ethyl? Couldn't you equally pull an H off the methyl? Well, indeed you could. Indeed you could. If I was to draw that, I'm going to draw the methyl as a CH2 and have an H off of it. Okay. Well, actually, why don't we draw H2C and focus on one of the H's off the methyl. And we react that again with water. Well, water acts as a base in this case, and it goes for the H. right? It attacks the H. So now I can draw a transition state. This time I'll put the water on the right. And I'll switch to red. For bond forming as it attacks the H. This bond is breaking. Double daggers to represent transition states. Now I need red again to show one more bond forming. So I have bond forming. And I have a bond breaking. That's the blue one. Again, the carbocation, delta plus, is disappearing on the C of the carbocation. That's this carbon that bore the positive charge over here. We have a delta plus on the oxygen. So because we have two transition states, let's label them transition state 2A and transition state 2B. Right. Now, once I'm done, I once again have H3O plus as a product. But this time, CH2, double bond CH, CH2, attach that CH2 as a CH3. Now, attacking the two different beta carbons, the hydrogens of the two different beta carbons, produce different alkenes. Notice that we produced when we attacked in the uppercase 2-butene, but in the bottom case we produced 1-butene. Now, in some cases, we can actually identify major and minor products, and in this case, we're actually going to be able to do that. It turns out, in organic chemistry, that we can draw a simple trend to determine who's major and minor. I'm going to do that shortly, and so we want to keep this in mind, and we'll come back to it to identify who's the major and minor product. What I want to do now, though, is to list the key features of the E1 mechanism and talk about them. Right? So let's do that. What are the key features? Many of these key features are similar to what we did in the SN1, and as such, will not get extensive explanation here, since we've already given it in the Scribblecast for the SN1. The first key feature, of course, is that the reaction is unimolecular. What does unimolecular mean? Unimolecular means that the rate of formation of the transition state in the rate determining step, rate determining meaning slow step, is controlled by only one of the reagents. In other words, only one of the reagents affects the rate of reaction. Now it turns out that the slow step, of course, is carbocation formation. Carbocations are hard to form. Once they're formed, they're so reactive that the nucleophile which attacks it, or in this case the base that attacks fairly rapidly. And so step 1 is our slow step. Because step 1 is a slow step, only it affects the rate of reaction. And since only one of the reagents is involved in that slow step, that is the alkyl halide, only changing the concentration of the alkyl halide affects rate. We discussed this quite thoroughly in the SN1 reaction mechanism, and so I'm not really going to go any further than that with it in the E1 mechanism. Our step 2 will be very closely related to step 8, or key feature 8. I shouldn't say step, I mean key feature. Key feature 2, the reaction involves carbocations, involves carbocation chemistry. I'm going to just say carbocations. It involves carbocations. Now I believe in the SN1 we said intermediates, but I'm going to split that off because some mechanisms don't always have carbocations as intermediates. So this mechanism both involves intermediates and involves carbocations, and the carbocation is the intermediate. So you might say that's redundant, but that's okay. Carbocation formation is rate determining. Carbocation formation is a slow step or rate determining. Carbocation formation is rate determining. Okay, key feature 4. The reaction is not stereospecific. Some of these we're going to leave to explain until after we've written down all the key features. Number 5, key feature number 5, there is no kinetic isotope effect. What does that mean? Well, we're going to have to explain that one once we understand what a kinetic isotope effect is. So we may actually be leaving that feature for the moment. 6 is quite obvious. It's a multi-step process. The mechanism involves many steps. And this is very similar to what we observed in the SN1. Let's try 7. Rearrangements, if possible. There are rearrangements that occur. rearrangements occur if possible. All right, rearrangements occur. We also have, and 8 really relates to number 2 very strongly. Sometimes they're combined. We have short-lived intermediates. The mechanism involves many short-lived intermediates. And remember, intermediates are not short-lived intermediates. I'm going to stop it there. Intermediates. Short-lived intermediates are involved. They are not transition states. There's a distinction between the intermediate and transition state. The transition state is the highest energy structural form observed in the transition. Intermediates exist in the valleys in the potential energy diagrams that describe the energy of the transition of the reagents and the products. So intermediates are energetically more stable than transition states. They also tend to have longer lifespans, longer lifetimes. I've used the term no finite lifetime for transition state, and I understand that can be debated. But the point is, transition states are fleeting, and they are just that, transitions. See, each structural change in the transition state occurs in a unit of time, whereas you can actually exist as an intermediate over a period of time. Now, number 9 looks very similar to what we saw for SN1, but it will need a little explanation. Tertiary reacts much faster than secondary, and that reacts faster than primary. We often find that, and I will accept just tertiary is faster than secondary. That's good enough. Primary is much faster than methyl. Can you guess why? That's pretty obvious. You need at least 2 carbons to make a double bond, and methyls only have 1 carbon, so they can't undergo this mechanism. And then we conclude overall the reactions favored by A, weaker bases, of course you can't be too weak. Weak is a relative term, so don't misinterpret that statement. Weaker bases compared to the type of bases we're going to be seeing involved in the E2 reaction mechanism, and we'll explain that. B, polar protic solvents, polar protic solvents help to favor formation of the carbocation. Ions are more soluble in polar protic solvents, and as a result, ionization is promoted by the presence of such solvent. And lastly, this is typical of elimination reactions, higher temperatures. When I say higher, it will vary by what I mean higher. Tertiaries, for example, may not need anything above room temperature, whereas you may be in the hundreds of degrees Celsius as higher temperatures for primaries. So it really depends, and so that varies quite a bit. Okay, so there you have the key features for the E1 reaction mechanism. Let's go through and look at some of these if we can. The first one, unimolecular, we've already mentioned. Well, carbocations, intermediate forms in the first step of the unimolecular reaction, and so point 2 is pretty obvious, key feature 2. Key feature 3, We've somewhat mentioned this already. Carbocations are not favored molecules. The structure is sp squared. The molecule, or in the carbocation ion, has an empty 2p orbital. It's short 2 electrons. These are reactive species, and they are usually very short-lived. Longer lived than transition states, but quite short-lived. So carbocation formation is going to be slow, not favored. And because of that, it's rate determining. It is a slow step. When we're going to come back to stereospecific and kinetic isotope effect when we look at them in the E2 reaction mechanism. The only thing I'm going to say with regard to stereospecific is let's draw a carbocation and consider, if we can, the two possible attacks. And I'm going to look at one of them. See if I can draw this here. And I'm going to make this ethyl group chiral. Turning one of the H's to a deuterium. So this carbocation has an empty 2p orbital here. That's badly drawn. And when this H over here leaves, that's going to make a 2p orbital. And that'll create my pi bond. And right now, the CH3s are trans to each other. And that would yield a trans product. Now, if I was only able to get the trans product, the reaction would be stereospecific. And we'll define that properly when we look at it in the next Scribblecast, when we do the E2. But I can rotate around this bond. And conformational change around a sigma bond is fairly fast at room temperature. And if that happens, I would get this guy. Of course. Still have our H here. Still have our methyl here. But this time, the H would be down. And if I rotated that way, the methyl would now be over here. And the deuterium would be over here. Now if I draw my 2p's, my empty 2p's for my carbocation, okay, that's the empty 2p. When this H leaves, okay, this H is going to leave. When he departs, I'm going to get a 2p alignment. But this time, look where the methyls are. They will be on the same side. So, because there's conformational rotation about here, whether the methyl is trans, the two methyls are trans in the alkene, or the two methyls are cis, will be random, depending on when the base comes in and pulls the H off. If the base comes in and pulls the H off when it's in this orientation, you get cis. When the base comes in and pulls off this H, you'll get trans. So the reaction is not stereospecific, which means basically that if you have a specific chirality to start with, you won't get a specific stereoisomer. You don't just get E or just Z alkenes. So the reaction's not stereospecific. Okay, no kinetic isotope effect. We're going to leave that till we can explain it in when we look at what a kinetic isotope effect is. So we will be referring to that in the E2 reaction mechanism. Key feature number 6, it's a multi-step process. Well, that's pretty obvious. We had steps 1, 2, and 3, ionization, rearrangement, and base attack. Step 7, key feature 7, key feature number 7, rearrangements. We've discussed that. This has to do with the stability of the carbocation. And if the carbocation can rearrange and get to lower energy before it's attacked, it will do so. This is often referred to as 1-2 shifting of groups. And we looked at several examples of this in the SN1 Scribblecast. So please refer back to the SN1. Key feature number 8, we have short-lived intermediates. Short-lived intermediates are involved here. And lastly, key feature number 9, tertiary is faster than secondary, who's faster than primary. Well, clearly this trend parallels the trend we saw in the SN1. This is caused by, again, the stability of the carbocation. If, for example, I compare a tertiary carbocation, like tert-butyl carbocation, you will recall, if I compare that, say, to a methyl carbocation, you will recall that in the case of the methyl carbocation, being that there were just hydrogens, there was less electron density from the substituents to stabilize the positive charge. In the case of carbon, carbon was larger with more available electrons. It's more polarizable, better able to donate electron density through its sigma bond. Effectively, this helps stabilize the positive charge. Now, for this semester, that's all you had to know, and it was referred to as inductive electron donation. The other two factors, steric assistance and hyperconjugation, will be looked at next semester. All right. Overall, the reactions favored by weaker bases. Weaker bases simply allow time before base attack occurs. Time for step 1, the slow step to occur, ionization. Polar protic solvents help solubilize the ions that form, again favoring the first step, ionization. And higher temperatures are typical of elimination reactions. And when I say higher, it's compared to substitution mechanisms. All right, having looked at this E1 mechanism, we're ready to go on and examine the E2 reaction mechanism and look at some of the key features that we haven't considered here, because in the E1 mechanism we will see that, E2 mechanism we will see that it is both stereospecific and has a kinetic isotope effect. And that will allow us to better understand what is meant by key features 4 and 5. Right, what I want to do now is just go back to our product distribution. In our reaction, okay, and now I'm going to draw a reaction instead of a mechanism. I think I had a ethyl here. And I had an H. And a methyl. There was a bromide. And we were reacting that with water. I'm going to use a triangle to symbolize higher temperature or heat. And the reaction went E1. And we were doing E1. We'll be discussing the point that alkyl halides prefer not E1. And so I'm basically producing a hypothetical situation here. If we want to we got carbocation, and we ended up getting 2 alkenes. We produced this alkene, 2-butene, and we produced one butene. Now, I indicated that you would be able to determine who's major minor here. And the way to do this is by a rudimentary understanding of the stability of alkenes. If I were to draw a stability of alkenes trend, lower energy, more stable alkenes are those whose carbon-carbon double bonds have more substituents. What do I mean by that? Well, I'm going to use R to symbolize an alkyl group. So R could be methyls, ethyls, isopropyls, any kind of alkyl. Carbon-carbon double bonds that have 4 alkyls are more stable than carbon-carbon double bonds that have only 3 alkyls. This is more stable than carbon-carbon double bonds that have 2 alkyls. And this would be the same as, okay, this is approximately equal to this. Actually, let's make it trans. Trans is a little better. Okay, and those are more stable than carbon-carbon double bonds that have 1 alkyl group, which of course is more stable than ethene. And when I say more stable, I'm simply meaning lower energy. We can determine this by looking at the heats of hydrogenation, and we'll be actually looking at how this is done when we do alkene chemistry in the next little while. Well, what does this have to do with which carbons predominate? Well, if the more stable alkene is major, this is referred to as Sayseff elimination. Sayseff elimination simply states that the more stable alkene is major. Now, Sayseff elimination doesn't always occur. Sayseff elimination can not occur sometimes. But when it does occur, the more stable alkene is major. How do I determine that? Well, what I can do is draw a little circle around my double bond. And I can ask, how many alkyl substituents are off of the double bond? Who has the more alkyl substituents? And if I look at the top 2-butene, I see there are 2 alkyl substituents off that double bond, where both are methyls. When I look at the bottom alkene, I see that there's 1 alkyl substituent, an ethyl. The one with the more substituents is more stable. Usually, Sayseff elimination is what predominates, and in this case it does. And you will always assume Sayseff elimination occurs unless I give you a special exception. Sayseff elimination occurs in this case. So 2-butene, because it's more stable, an alkene, is actually major. And you can indicate that. Whereas in the 1-butene, we would indicate it's a minor product. Now always remember that elimination occurs in competition with substitution. In addition to these major-minor alkene products, even when you favor conditions to drive elimination, there will always be some substitution product. Trace amounts of it in solution. That trace amount will vary depending on the reaction conditions. Well, there you have it. That's the E1 reaction mechanism. In the next Scribblecast, we're going to take a look at the E2 reaction mechanism. Thank you for listening.